Okay.
You want me to?
Yeah.
Just double check. Yeah. Okay. I think we're good.
Okay. Nice. Thank you. Hi guys. Can everyone hear me fine? Yes? Is this mic working? Hello? Nice. Thanks. So we're just going to go ahead and get started with this final review session. Again, for those of you who just got here, these slides are posted on the 61B Piazza underneath the note CSM final review session. There should be a link that allows you to view these slides in view only, so feel free to follow along as we go through this final session together. All right, so while you guys do that, let's go ahead and get started with the overview. So today we're going to be going over midterm 1 and midterm 2 course stuff. So this includes inheritance, dynamic method selection, casting, asymptotics, overriding, overloading, interfaces, abstract classes, exceptions, hashing, autoboxing, binary search trees, 2-3 trees, left-leaning red-black trees. Also, my apologies. I have this earphone plugged into my left ear, so I can't really hear that well. It's only from my right ear. So if you have any urgent questions, like raise your hand violently in the air, or like jump up and do a jumping jack or something, get my attention. Also, you can also shout out my name. My name's Alan. Nice to meet you guys. I'm a senior mentor for CSM, so nice to see y'all here. All right, I'm going to go ahead and get started. So if you haven't done so already, please pull up the slides on Piazza, and it should be view only so you can follow along. So inheritance and classes. In Java, when we say class B extends class A, we can then, with this terminology, say that A is a superclass or parent class of B, and B is a subclass or child class of A. Hopefully this should be review for everyone because you have been coding in Java for the past semester, so that's fun. All right, also, what it means for a class to be a subclass is another, is that a subclass inherits all the methods and variables from their superclass. So that means all the methods are public and not private, the subclass has access to. So you can call those methods in the subclass. Also, quick note, Java does not support multiple inheritance, which means you can only extend one class. So for instance, when you declare your class like pelican extends bird and mammal, you can't do that. You can only extend one class. But you can implement multiple interfaces, which is kind of the confusing part. But we will be going over those differences later on. Do I have any questions? Yes. Okay, so his question was, if there is a private method in a parent class, do subclasses that extend it inherit those private classes? No, you cannot call those private classes because the private keyword basically means you can only call that method or look at that variable within the same class. Any other questions? Okay, also for those of you who just got here, these slides are posted again on the Piazza, so feel free to pull up the CSM final review session note, and there should be a link there letting you view these slides in view only. All right, let's move on. Static and dynamic types. So a static type and dynamic type are two types that we can associate with every single variable instantiated and declared in Java. So the static type is basically what's to the left of the equal sign, and it's basically the type that the compiler knows during compile time. And the dynamic type is to the right of the equal sign, and this is what the program knows during runtime. Also, another observation is that the dynamic type must be the same class or a subclass of the static type. In other words, dynamic must be less than or equal to static. It's kind of a nice way to think about it. And the main advantage that we have with these static and dynamic classes is that we can, in Java, utilize this thing called dynamic method lookup. Basically, in Java, whenever a method is invoked, dynamic method lookup occurs. And this occurs after compiling, which is runtime. And basically what happens during compile time in the compiler runs through all of your code, and then it looks at the static type. That static type is a class in Java, and in compile time, we basically ask ourselves, does this static class have a method called this, whatever you're invoking, that can take in these arguments of the same type or same quantity or whatever, right? So that's what's going to happen during compilation. And if the static class does not have that method, you will get a compile time error. So on your exam, when you encounter these questions and you're presented with the question like, does this code compile? Look at the static type for each of the variables that invoke these methods. And if that static class does not contain a method that is of the same name and can take the same arguments, then you will get a compile time error. This seems like a lot of words to your face right now, but we will be going over examples that are really fun because I designed them myself. Yes? Yeah, so he just asked, when we call a method and we look at the static type of the arguments, is it okay if the static type is a subclass of the arguments that could be taken into the function during the, when the function's running? Yes, that is okay. And again, we will be going over examples that may throw you off, but we're all here to learn, and ultimately that is what class is for. So, very good question. We will be diving into that later. Any other questions? Nice. Oh yeah, also, if at any point, if you're hungry, we have chocolate chip cookies and oatmeal raisin cookies up here, so just run on up and get your cookie. We might not have one for everyone, so if you're not that hungry, try to take like half a cookie or a quarter of a cookie, whatever's fine. Okay, so moving on. Again, that is what happens during compile time. We check to see if the static class has this method that can take in these arguments. After that, during runtime, we're going to be doing dynamic method lookup. And basically what this is that we prioritize methods of the same name that take in the same type of arguments in the dynamic class and also in parents of that dynamic class all the way up to the static class. This is also known as overriding, right? Over here, I have kind of pseudocode written down on how we use dynamic method lookup. So when we are at runtime, it is implied that we compiled A-OK, everything's fine. This means that the static type does have the method that is getting invoked as well as a method that can take in those arguments. So let's call C the dynamic type of the variable. And while C is not equal to the static type, we're going to check to see if the class C has this method that can take in those arguments and of the same name. If at this point we do find this method, we're going to use this method, and we're going to terminate this little algorithm going on. Else, we're going to set C to equal the parent or superclass of C and check to see if that class has this method. If it does not, we keep going and going and going until we hit the static class. I'm going to be referencing this pseudocode when we jump into these example questions. So it might seem a bit dry, but here we go. So question number 1. Up here we have this inheritance structure. We have an interface person, and all people sleep. There are 2 different people, students and professors. There are 2 types of students, engineering students and Haas students, and there is another subtype of engineering students called a CS student. Over here, we see that report sleep as a function is overridden. Like the report sleep function in engineering overrides the student one. The report sleep function in Haas overrides the student one as well. This is basically what it means for when you extend another class. So my question to you is, what will these calls over here in the bottom right output? Again, to the left of your equal sign is the static type of a variable, and to the right over here is a dynamic type. So for variable S1, the static and dynamic type are both student. So I'll give you guys 5 minutes to work on this question. Feel free to talk to your neighbor, tell a joke, get a cookie. 5 minutes, guys. All right, guys, let's reconvene. So please, shh, 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 shh. All right, my first question to you guys is, which of these lines do not compile? Trick question, they all compile. Nice job. So let's just go with the first line, s1.report sleep. So we check during compile time for the static class of student1. S1, which is student. So does student class contain a method called report sleep that takes in no arguments? Yes, it does, up here. So therefore, compile is okay. Next, at runtime, we check to see if we can use dynamic method lookup. But we just found out that these static and dynamic type of S1 are the same. So therefore, the only method that we can invoke is the one chosen during compile time. Therefore, we output 6 hours a day. Very healthy. Very nice. All right, so S2. In S2, when we do S2.report sleep, we're going to first check to see if this line even compiles. What is the static class of S2? Student. Does the student class contain a method called report sleep? Yes, it does. Therefore, we are okay with compiling. Next, in runtime, we check to see if we can use dynamic method lookup. So right now, we have that S2, its static type is student, and its dynamic type is host student. So if we go back over here, we're basically going to see if host student, the dynamic type, contains a method called report sleep. The exact same method in terms of same name and same arguments and same type of arguments. So we find out that we do have this method called report sleep that overrides the report sleep in student. So when we run s2.report sleep, what will we be printing out? 5 hours a day. Not much of an improvement. So next, we have s3.report sleep. The static type of S3 is student. The dynamic type is comp-sci student. So therefore, does this line compile? Yes, because the static type student has a method called report sleep. Now, during runtime, we're going to try to use dynamic method lookup. So we're first going to check the class comp-sci student. Does comp-sci student have a method called report sleep? No, it doesn't. So we're going to traverse up the inheritance structure and go to its parent class, which is engineering student. Oops. Does engineering student have a method called report sleep that takes in no arguments? Yes. Therefore, we stop there and we use that one. Therefore, we print out what? Exactly, because we don't know what sleep is. Yes, question. Wait, I wasn't following from the beginning. Could you repeat that?
Yeah, so if you set if you set the static type of S3 to engineering student, and you remove report sleep from the engineering student class, would you get a compile time error in S3.report sleep because the parent class doesn't have report sleep in it?
Yeah, so his hypothetical was, what if we change the static type of student 3, S3, to be engineering student? Right, and then we removed report sleep from the engineering student class because engineering students do not know what sleep is. Would this compile? So as with all questions of will this code compile, you always have to check the static class of the method invoking this method, right? So in that case, the static type of S3 would be engineering student, and because we removed report sleep from that class, it will not compile. Yes. Yes, question. Okay, so his question was, if we made the report sleep function in the student class private, would s2.report sleep compile? The answer is no, because the private keyword basically means that only objects of that class are allowed to call it and use it, right? But if we wanted to extend it to the subclass, is there a word that allows us to do so? It also starts with a P. Yes, use protection, protected. So you would have to do protected int or void report sleep, and then you would be able to inherit that. Yes?
Also, if you made that private, like in the student class, it would not compile because it doesn't have the same signature as the interface, or does it not have to have the same signature?
Okay, so again, this is a question. He asked if we made this private, would this even compile? Because the interface specifies public void report sleep, right? And if you implement an interface, you have to have the exact same signature. So yes, if you change report sleep to be private, you would get a compile time error, but a different type of compile time error because you didn't correctly implement the method specified in the interface. Yes, question in the back? Can an interface be a static type? Okay, so static type basically means that we are declaring a variable, right? Because it's to the left of something. So can you declare an interface as a class? No. Therefore, interfaces can never be a static type. Yes?
In the earlier hypothetical example, you would get a compile time error, but like, why wouldn't, I know it's called dynamic method lookup, but why can't you look up in the static method? Like, why can't you look up in the static type? Because the static type also extends another class that has a method in it, so wouldn't Java be smart enough to look that up?
Okay, so it's being answered in the audience now, but his question was, in that earlier hypothetical statement where we had engineering student to be changed as a static type of S3 and where we removed report sleep, why isn't Java smart enough to look at the dynamic type and see that it does have a method called report sleep? And that question lies with Oracle because they're the ones who designed Java. Unfortunately, Java compilers, all they are allowed to check is the static type of variables. The compilers only know the static type of each of the variables you have.
I think what I was trying to ask was why can't it look up to the classes extended by like engineering student, student itself, which has a report student sleep method?
Okay, so his question was, even though engineering student extends student, why can't we just look up to see parent classes that have this method and therefore we might be able to compile? So this is bad programming practice because sometimes we have these inheritance structures and they might not even make sense. Like they might not be as intuitive as like engineering students are a specific subclass of students. For instance, you might have like exceptions, and then like you have different types of exceptions, like no pointer exceptions, class cast exceptions, everything of the like, right? But if you declare your variable with your static type, you're basically limiting your zone of search to this specific thing, right? So as a programmer, it's nice to have these abstracted away in the fact that if we know the static class of a variable is this, if it does not compile, then we do know for a fact that that means the static type does not have this method or variable.
So there's no such thing as static method lookup.
There is no such thing as static method lookup, only dynamic time lookup. And I think you guys should take CS164 if you're interested in compilers and everything. It's with Hillfinger, which makes it exciting. Yes? Yes, just for clarification, during compile time, you only check the static class for these methods to compile. Any other questions before we move on? Because this gets even more confusing. The plot thickens. Woohoo. So casting, right? So we just spent the last few minutes talking about compilers and how they're kind of dumb in the sense that they only know the methods in the static class, and that's all they check for, right? So compilers only know the static type of variables. So for instance, if we declare S4, where its static type is student and its dynamic type is host student, then we declare another variable called S5, whose static type is host student, and we set that equal to S4. Will this compile? No, because compilers only know the static type of variables again, right? So when we set this equal to S4, it's going to look at the static type of S4, which is student, and not all students are host students. and therefore it doesn't really make sense for this to compile. One way we can get around this compiler thing is that we can use casting, which basically is a promise that we as programmers know what we're doing. And in a sense, we can traverse the compiler's rulebook, playbook, and force this code to compile. So for instance, again, we have the same situation as above. We have S4, whose static type is student and dynamic type is host student. If we wanted this line to compile, all we would need to do is put in parentheses the type of S4 in which it truly is. So this would actually compile, because luckily, S4 turns out to be a host student in the dynamic type. So at runtime, we won't be encountering any errors. But if we violate this trust that we have with the compiler, it's going to throw an exception, not during compile time, but during runtime. And that's called a class cast exception. So for instance, if we have S4 again, its static type is student and its dynamic type is host student, and then we declare an engineering student, S5, and we cast S4 to be an engineering student, well, if you are not in MET, or that program, whatever it's called, MET, it turns out that not all host students are engineering students, and it doesn't even follow the same structure in the tree. So for instance, when we have this code, it's going to compile, and if we were to call a method with S5 that is a method in the engineering student class, basically during runtime, Java is going to look at the engineering class, realize that that method is not in here, it's actually in host, because S4 is actually a host student. That's when we get a bad cast exception. Any questions? Again, as we move on to these next set of questions, keep in mind that the compiler only knows the static type of these variables. And as a result, when we're passing in arguments to a function, we only know its static type. Yes, question? So this was a bad example on my part. Turns out this is actually okay, because engineering and host have the same function names. But if you have like engineering students like go to Mechie class, build a robot, like these are two functions in engineering, right? And in host, it's like handle the business side and throw parties or something like that. These are two completely different functions, right? Not trying to throw shots or anything, but because these are two different methods, you run the risk of violating the compiler's trust with bad casting, in a sense that if you do call this argument that is expected to be in the dynamic type, then you're going to get a bad cast exception. Yeah, because it's going to look in the engineering student for throw party, and I'm pretty sure engineering students can throw parties too, but they'll be different, like homework parties. But again, bad jokes. Sorry, guys. Any other questions? Great. Oh, wait, yes. Yes. So if at any point we use S5 and we call these methods, you then run into compile type errors that may occur because we're going to be looking at engineering student class to see if these methods can compile. Question?
So we said earlier that in this example, it will actually like run because they have the same method name. But what would the method that run, like in which class would the method that's run in the end be from? Is it going to be from engineering student or is it going to be from host student? Because host student is what it actually is, but then engineering student is the container that it's in.
So he's now asking, the question was, which report sleep do we use now that they're both the same thing? The answer is, I don't know, but luckily there is a really cool website called repl.it, so repl.it. What you can do is basically load up your code over here and you can play around with what happens. I didn't have the free time to do that before, but that seems like a really cool question. All right, so let's move on to these examples. So the first question is, which of these lines throw an exception? I'll give you guys 2 minutes. Does anyone want to volunteer an answer? All right, right there in the back. Yes, so then S3 will not compile because the static type of S3 is engineering student. So in memory, you can just basically think of it as like a box that can hold a pointer to an engineering student. We casted S1 as an engineering student, but let's be sure to see if S1 is actually an engineering student, which it is not because S1 is just a regular student, right? So therefore, that will not compile. Also, S3.reportSleep will also not compile. So for these next 5 minutes, I want you guys to think about S4.reportSleep and S5.reportSleep. These are pretty challenging in my opinion. Yes? It's because the static type of S1 is student. Yes. Oh yeah, sorry. Not a compile time error, but a runtime error. Sorry, just a regular exception. Mhm. So sorry, I misspoke. Earlier I said that which of these lines throw a compile time error, but actually I just meant which of these lines throws an exception. And it is S3. Good luck, guys. It does compile. But then you might have a runtime exception. Casting down. Casting to a subclass. Can you give me an example? Uh-huh. So it will compile because casting will basically force it to compile, right? But then during runtime, if you do find out that this variable that you cast it to does not have the method you're looking for, then you're going to get a class passed. What? Valid cast is what you're talking about. So the only valid cast that is very general is casting to a more specific type. So for instance, like if you look at S4, the way it's casted, that's a perfect cast. So we have a pointer, its static type is engineering student, and we also have S2, right? S2, its static type is student, so without that cast, that wouldn't have worked. But because we casted it to engineering student, it will work because it actually turns out that S2's dynamic type is engineering student. So it's okay. So oh yeah, then that's just an extraneous cast and it doesn't, like it's okay, but like it's unnecessary. Yeah. Are engineering students animals? So animal is not related in any way to this inheritance structure, so you would get a bad cast. I think at compile time, it will recognize that this cast is in different inheritance trees. Regardless, you will be throwing an error. Whether it's compile time or runtime, you can be able to you can probably find out for yourself.
So for example here, like S1, it's a static type in student, right? And engineering student is a subclass of student. So basically we are like casting S1 to its subclass, and or like we can like say in another case S1 is an engineering student and we are casting to student, like this is like casting up. So like either casting it to its subclass or casting it to its parent class. And as far as I know, like both of these are valid cast. So they're like, so for example, what if I cast it to a totally unrelated class, like
Oh, okay, I have a few more minutes, but yeah, what's up?
like yeah, just like I said. So if I cast it to its parents class or to its subclass, then it's a valid class, right? But what if I cast it to an unrelated class?
So if you were to like cast engineering as a hot student, so it would correctly compile, but you might run into runtime errors. So this
Okay.
is what these two were talking about earlier.
Oh.
In the hypothetical statement where like we removed this and this, basically if you cast incorrectly in different branches completely unrelated in the same level, you might get a runtime exception.
So as long as the holder, like the type that you are trying to cast matches the static type of your like holder, then it's always a valid cast in the runtime. Sorry, in the compiling time, right?
Yeah, so you can cast correctly.
But it may cause like arrows
Yeah,
in runtime.
but then a good cast, I think, is what you should be thinking about. A good cast is basically when you cast something that is either the same class or a subclass of the static type, right?
Yeah.
Because
That's a good cast.
shoot, what was I gonna say? So in this example, like we didn't know if S1 was truly a student or an engineering student,
Yeah.
right? So this cast in S3 is a bad cast because it turns out that S1 is actually just a regular student and
Yeah.
not an engineering student.
That's a bad one. So it can potentially cause error in runtime. But this is a good cast.
Yes, it is a perfect cast.
In the runtime, like when you compile, like it goes through, like it all works fine. Like there's no compile time errors. I'm like confused. Like when you're talking about runtime errors, would you get the error when you're at the assignment statement? Like do you like go through the code twice as a compiler?
No. So then compile time, check to see if the methods are okay, right?
Yeah.
But then runtime is basically, these exceptions are only thrown when you find that the method is not, when you incorrectly invoke the method, in
Okay.
a sense.
So
And that would be a bad cast.
so when you do S3 dot report sleep,
Uh-huh.
is that like where the runtime exception happens?
Yes.
So then
I just made a really poor example with this question and kind of butchered it and kind of named all of the function names the same. But in the future, I should probably change it to like the two different things
Okay.
to like clarify it. But yeah, like
So-
I'm sure that like, so for S3,
Yeah.
S3 has static type engineering student, right? But engineering student also has the report sleep.
Yeah.
But it's a question of whether or not we use the student report sleep or engineering report sleep.
Right.
And that's what would throw the runtime exception.
Okay. So you said you cast engineering student to you cast S1 to engineering student even though it's just like a regular student.
Mm-hmm.
And so because when you do S3 dot report sleep, the compiler doesn't know like
Yeah, but then when it actually accesses that object in memory,
Yeah.
it turns out to be just a regular student.
right. Oh, I
Right.
see.
Whether or not it has a report sleep function, we don't know.
Oh,
but
so
if
it doesn't matter because
yeah,
like you kind of forced like the wrong class onto like the wrong
Yeah.
static type.
you're forcing it to be someone that doesn't want
not.
to.
Yeah, I get that. Okay, so like then when you do S3 dot report sleep, then it like realizes, hey, it's not.
Do you mind if we
Yeah,
carry
yeah,
on?
I'm
Yeah,
sorry.
we're running really low on time. Yeah. All right, guys, let's reconvene. So again, S3.report sleep does not compile. Let's take a look at what S4.report sleep returns. So what is the static type of S4? Engineering student. Does engineering student contain a function called report sleep? Yes, it does. Therefore, it compiles okay. But even more importantly, S4 has been casted to an engineering student. I mean, S2 has been casted to be an engineering student. The static type of S2 is student. So without this cast, it wouldn't have even compiled. But because at runtime we use dynamic method lookup, when we access this object in memory, we're going to be looking at this variable's dynamic type, which is engineering student, which all in the end turns out to be okay because the static type of S4 is engineering student as well. So therefore, what will we output? What? Oh, okay. That's the answer for S5 too. So what is the static class of S5? Students, right? Student contains this function called report sleep. Therefore, we compile okay. Student has been casted. S4 has been casted to a student, which is okay because student is a subclass of engineering student. superclass, my bad, superclass of student, right? So therefore, when we look at the actual type of S4, it's engineering student, we jump to that class and use its method report sleep. And therefore it's what? Yes, question. Yes, it would have compiled even without the cast. Yes. Wait, what? Yeah, so earlier I misspoke. It actually is a runtime error. Yep. So the question is, can you explain why S3 throws a runtime exception? So I will walk through this process with you. So this was a bad example that I designed in my part because report sleep is overridden in all these classes. So the static class of S3 is engineering student, right? S1 is casted to be an engineering student because S1, it's actually the static and dynamic type are both student, right? But then not all students are engineering students, so that is one, a bad cast, but it still does compile because casting allows us to run through this compile time error and just jump straight to execution. But if we were to call a method in engineering student that with S3 that does not exist in the student class, then and only then do we get a runtime exception. Yeah, so in this case, yes, it does turn out to be okay, but whether or not it's a question of which report sleep we use is a mystery because this S1 is an object in memory. It's a student class. But we treated S4 as an engineering student class, right? However, they both have this function called report sleep. So again, this is just a bad example, but I probably should have changed it. You can run it on repl.it in your free time. Right now, we're going to move to overloading, which has its own plethora of questions as well. So any last-minute questions that I can run through, you can talk to me during the break time too. Okay, so overriding and overloading. Wait, what? Okay, I thought I heard someone call my name. Okay, so overriding happens between methods of the same name and type of arguments across different classes. So it's same name, same arguments, but different classes. Overloading, on the contrary, happens between methods of the same name in the same class. Therefore, these methods that are overloaded are the same name, but different types of arguments, different quantity of arguments, but they're all within the same class. So in this example over here, which methods are overloaded? Yes, so in the fruit bat class, we have two methods called eats. They are of the same name, but they take in two different types of arguments. One is a fruit, one is an apple. So these methods are overloaded. Which methods are overridden? Yes, eat fruit. So eat fruit in fruit bat overrides the eat fruit in mammal, and eat fruit in mammal overrides the eat fruit in animal. Yes. So if you have the same method name, argument names, and argument types in different classes, that's overriding. Overriding. Yes. Different classes overriding. Question in the back? Constructors, usually with these subclasses and inheritance structures, constructors are the ones that are usually overridden and not overloaded. But I'd imagine that maybe you could overload a constructor. Yes, yes, that's a good example of overloading constructor methods. So for example, you might have a constructor that takes in no arguments. You might have a constructor that takes in 2 apples. You might have a constructor class that takes in 2 pelicans, all within the same class. Those are all overloaded. Yeah.
Can I say that the E apple A is overriding the E through F of mammal?
No, you cannot, because when you override a method, they have to take in the same type of arguments as well.
But like E apple A is overloading E through F, which is overriding E through F of mammal.
The bottom line is when you override a method, it has to be the same name and same type of arguments. Then and only then can you override a method in the subclass. All right, so take a look at these 2 questions. I'll give you guys 3 minutes. We're running really low on time. We still have to cover like left-leaning red-black trees, BSTs, and all that other fun stuff. So if you have any questions on inheritance, just talk to me during break. How are we doing on power?
I can't see the.
Okay.
I don't know. I'll just post it.
Right, because like it goes off the inheritance tree, you can't find it.
All right, so let's quickly go over these 2 questions. So in compile time, we check to see if the static class contains this method being invoked. So the static type of A1 is animal. Does animal contain a function called eat that can take in the static class of F1, which is fruit? So does animal class contain an eat function that can take in fruits? Yes, it does. Right, up here. So when we run this, we try to use dynamic method lookup. So earlier we chose this function. Yes, it does during compile time. Is there a method with the exact same name and same type of arguments in the mammal class? Yes, it's right here, the eat fruit f. So we can therefore say that the eat method in mammal overrides the eat method in animal. And therefore we would use this and print out mammal eats fruit. Any questions? Yeah. Okay, can you ask me this question again after we go over the second part? Because I think that's exactly the case you're looking for. Yeah. Okay, so part 2 of this question. Now we're going to run a1.eatf2. So does this code compile? The static class of animal is a1. The static class of a1 is animal, and the static class of f2 is apple. So does the animal class contain a method that's called eat and that can eat an apple? Yes, it does, because animal is a subclass of fruits, right? So because apple is a subclass of fruit, mammals are not fruits. Sorry, been watching too much Animal Planet, but it's fun stuff. Planet Earth 2 on Netflix is an amazing show. Quick plug. So yes, in the animal class during compile time, we found this method called eat that can eat an apple because apples are fruits. So we choose this method called eat that takes in static type fruits. All right, so now during runtime, we're going to look to see in the dynamic class of A1, which is mammal, do we have a method that is exactly the same as the method that we chose during compile time, which is namely called eat and takes in a fruits. Yes, we do. Right here, eat fruit F. So again, we print out mammal eats fruits. The goal of this question was basically just to see, even if the static types do not disagree, if the static class supplied to the argument is a subclass of the argument specified in the class, that would be okay. Yes? What if the animal class contained an eat method that can take in an apple? Then we would choose that one. And then during dynamic method lookup, we would check to see in the mammal class, does the mammal class contain a method called eat that can take in an apple? No, it does not, because it only has an eat method that can take in the fruits. So therefore, we would use the eat method in the animal class that can take in an apple. Yeah. So can you ask me that question again after we go through these next iteration of questions? Because I think I covered that case too. Yeah, so let's move on if there's no questions. Beautiful. You guys are all beautiful. All right, so over here I have 2 more questions. Go ahead and take 3 minutes to work on this. We're running pretty low on time. I shouldn't have taken an hour to go through this, but it's nice that you guys are learning, so keep up the good work. So 3 minutes. All right, guys, let's reconvene. So, in this line right here, a1.eatf2, we check to see if the static class of a1, animal, contains a method called eat that can take in the static class of f2, which is fruit. Which is apple. The static class of f2 is apple, guys. So, we look into the animal class. Does this class contain a method called eat that can take in an apple? Yes, it does. Eat fruit f. So the compiler determines that during execution, we are going to be using this function, eat fruit f, if the dynamic class or a parent of the dynamic class contains a method that overrides this function. If it does contain a method that overrides eat fruit f, then and only then are we going to use it, right? So the compiler says we are going to be using eat fruit f. If it gets overridden in any of its subclasses, then we may use dynamic method lookup to use that overridden method. So it compiles, okay, now it's runtime. So the dynamic class of f2 is apple, and the dynamic class of a1 is fruit bat. So we look at fruit bat. Does fruit bat contain a method that overrides the method that we chose in the animal class during compile time? Yes, it does. Eat fruit f. Therefore, we are going to be printing out bat eats fruit. Yes.
So earlier you said that there's no such thing as static type lookup or static time lookup, but here you're looking up from fruit to apple to fruit in order to satisfy the requirement of your function, your method in the animal class called eat fruit.
So I said there's no static method lookup. That's method lookup only, not argument looking up.
So you can look up arguments.
Yes. If you do, no, you can't look up arguments, but if you find a case where the function takes in a parent class of the arguments you supplied into the function, then that would still work.
But
So dynamic method lookup exists only during method lookup. Yes.
so why are you able to look up during static type checking then? Even though it's static type checking, you're still able to look up the class, like look up. But why are you allowed to look up the parameters, even though like you're not allowed to look up the method itself, like in the method class?
That's something you learn in CS164. But again, you only use dynamic method selection when you're selecting the methods you're going to be using after compile time. When you check to see which function you use that are overloaded, the static type of those arguments supplied into the function, if that static type is a subclass of the arguments specified in the class declaration, then you can use it. Yes. When would the dynamic type of an argument ever matter? It does not matter. Yes. Yes. You only look at the dynamic class when you're using dynamic method selection. Yes, that was a really good question. All right. Oh, okay. Okay, so A2, we forgot to do this last question. A2's static class is fruit bat. So does fruit bat contain a method that can take in the static class of f2, which is apple? Yes, it does. It contains this eat apple a function right here. So the compiler determines that we are going to be using this method, and if during runtime we find that it is overridden in one of its subclasses, potentially its dynamic type, then we will use that method instead. However, that is not the case because we have that A2, its static and dynamic class are the same, namely fruit bat. Therefore, when we run this line, bat eats apple. All right. So interfaces versus abstract classes. This is just a chart that you can probably write down on your cheat sheet. You can implement multiple interfaces, but you cannot extend multiple abstract classes. Interfaces have no constructor, but you can instantiate an abstract class. That being said, abstract classes can have class variables, but not instance variables. Okay. So interfaces do not have variables. You do not have to use a keyword for abstract methods and interfaces, but for abstract classes, you have to declare a method abstract if you don't want to provide an implementation. You use no keyword for concrete classes and abstract classes. You just go ahead and define what you want to do with that function. But in interfaces with Java 8, you have to use the default keyword to actually define a method in your interface. Yeah.
When you say concrete methods, for the use no keyword for concrete methods, you just mean like get implementable method just the way you usually do, right?
Yes. When I mean you use no keyword for concrete methods, basically in abstract classes, you can just implement a method as you normally do in a regular class. Yeah.
Since there would be no instance variable in abstract class theory, so does that mean we can only define a static method in the abstract class?
Yes. Static variables, again, are class variables too. And things that are not static, your objects, instances, as a class do not have access to. Just a definition of static. Yeah.
Wait, so but non-static variables can also be class variables, right?
Non-static variables can also be class variables. Non-static variables can also be class variables?
Wait,
No, because class variables always have the static keyword.
okay. So
Yeah.
like even if also
If you do a quick Google search, what does static mean in Java, I think you'll find what you're looking for. But bottom line is, you use static to define class variables. All right, iterators and iterables. So this is a common point of confusion. Basically, what an iterable is something that returns an iterator. And iterators are something that iterate through an array list, whatever you supply in. Right? Iterators, if you implement this interface, you have to have 3 methods in your class, namely a Boolean hasNext, eNext, which is just a type of the iterator with generics, and you have to have a remove too. I think this is new with Java 8, the remove part. Yeah.
why are the generics that the iterable takes different from generics the iterator takes?
Oh no, these are just 2 different screenshots that I ripped off from the internet. So 2 separate different examples.
Is the remove method necessary?
What?
Is the remove method necessary?
I think that's something new with Java 8, but I think in 61B, all you need to know is that you just need a hasNext and the next. So don't worry about remove. So yeah, both are interfaces. Iterators specifically, this is a common testing point for questions. Just define this new iterator, for instance, where given an array of dog objects, create an iterator that iterates through the array of these dogs from least to greatest weight. Basically, a general gist of how you would implement this is you would make a class called like dog iterator, and then in the constructor, you would take in that array, you would do some kind of sorting with the weight, and then make a new array, set that as a instance variable, have your pointers, and then as long as there is a next in the array, which is basically a dog that you haven't spit out in the iterator yet. Okay, spitting out a dog seems terrible. Then it would just return true, and next will return the actual object that is next in the array from least to greatest weight. Yeah.
You didn't mention that you have to implement iterator, but we do, right?
Iterators are interfaces. Do we implement or extend interfaces? Yes, so you have to implement iterators. Oh, shoot, I probably said extends.
No, you didn't
Sorry,
say
guys.
anything at all.
Okay. Sorry, long day, guys. Dead week. Okay, yes, last question.
For an iterator, if you go through next, so let's say you iterate through the entire array, then you can't call next again.
Yeah, so then the way iterators work is that you always call hasNext before you call next. And if hasNext returns false, then there's nothing else in your array.
Is there a way to restart the iterator?
Yes, there is. It depends on how you implement your iterator. So for instance, you can have something like in your construction of your class going like, if it is at the end and we want to make 3 rounds through the entire array, then we can just reset the pointer to be at the front. It depends on your instructions and your specifications and how you want your iterator to be implemented. What? Why would that cause an error? The remove method is basically like if you're in your pointer, like at this point in the array, and you just want to skip it. For example, like in our dog array, like we have an array filled with Shibas, and we only like Shibas, but we see a corgi in there, and we don't like corgis. You can basically say has next, and then you can peek at next, something like that. And then if you don't like a corgi, you remove it from the array. Okay, so you call remove, and then you call next. Will we error? Yeah, it's I think it's a special property of iterators that you can't. So you can't modify the direct copy of whatever you pass in, but I think you can modify if you make a separate, different array, for instance. Like if you want to iterate over like a dog array 3 times, you will be okay with creating a new array that is 3 times in length of these dog objects repeated. If there are no more questions, we now have my main man Tapan talking about pass by value, very important things.
All right, how does this work?
So put this here up here. The mic for the webcast is here, and
Okay.
the mic for the actual lecture.
Okay, great. Yeah, so like Alan said, my name is Tapan. I'm a associate mentor for CSM and a tutor for the core staff. So yeah, we're going to go over some like low-level Java conventions. So the first thing is pass by value. So yeah, pass by value. This is also referred to as the golden rule of equals. So this is basically when we pass parameters into a function. When we pass values into a function, we pass a copy when we're using primitives, and when we're passing objects, we pass a reference. So we'll look at an example to like get an idea of what this actually means. And then yeah, just know what the primitives are. They're here for your reference. Okay, so pass by value practice. So we have this example here, right? So we have the function simple swap. So basically, it looks like it's supposed to swap numbers when you input numbers A and B, and then it's supposed to switch A and B. So we have our main method that calls simple swap. So what is the printed output? So take like 2 minutes, and we'll come back and talk about this together. Okay, so the printed output. So like the first time we see the system out print line, we have x equals 2, y equals 5, and then we call swap on x, y. So when we call this, the second time we call print, we have x2 and y is 5. So this question is supposed to trick you up, right? So it's supposed to, calling simple swap, you'd expect x and y to swap their values. So yeah, here let's talk about why do the values stay the same. So the reason these x and y don't change values is because when we call simple swap, we pass in a copy of x and y. So we don't pass in the reference to x and y themselves, and as a result, the original x and y are unchanged. Okay? Does anyone have any questions on pass by value? Yeah.
Then how did we actually change them?
Good question. Yeah. So the question is, how do we change? How could we bypass this issue with pass by value? So a way to do this is so this happens if we pass in a primitive. So if we pass in a primitive, we pass in a copy. So we want to pass in a reference if we're calling simple swap. So a way to pass in reference is by passing in objects rather than the primitives. So we listed the primitives on the previous slide. So you can define a new object with a class, and then from there, pass these objects into simple swap, and as a result, we could change the values of x and y. Any other questions? Yeah. I see. We'll talk about that on the next slide. Yeah. Okay. Any other questions? Can we keep going? All right. All right, yeah, so we have generics and autoboxing. So first, what is a generic? So basically, a generic is kind of like an object version of a primitive. So like we usually see this kind of like notation with like this kind of thing where we put that when we define some sort of object. So like an example of this is like when you instantiate an array list, right? So when we call array list and we make a new object, we make a primitive into its wrapper class. So you can see we have our primitives right here, right? And then we have our wrapper class. So when we're turning a primitive into an object, we turn it into its respective object version. And yes, we can do that, what you were asking. Okay, so let's talk about autoboxing. What is autoboxing? So autoboxing is kind of the way that we turn a primitive into its wrapper class or its object version. So this happens automatically. So say if we add an integer to the array list that we defined here. When we add int to array list here, it turns into an integer, or the object version of the wrapper class. Okay, any questions about this? Yes? Yes, it would change the value, because then you're passing in a reference. Yeah. String is not a wrapper class, but it is an object. A string is an object, but it's not a wrapper class that comes from a primitive. Characters are primitives that lead to strings, I guess. Yes? Can you repeat the question? Alter a string. How would you like to alter a string? I guess you can like splice it. Yes. I see. Okay, so basically the question is, if we alter a string, do we change what the reference to the string itself? So I think like for some methods, this changes the value. So like splicing, I think it redefines a new string. But I think you can index into a string or something and change some of the characters within it, and that doesn't change a reference. So if you look at the different string methods under the Java dictionary, they'll tell you whether the method is a mutable change on the reference of the string. Okay? Yes? I think autoboxing will change this autoboxing, how we automatically convert a primitive into a wrapper class. The wrapper class will change into a primitive as well. Yes? Okay. Say that again? I see, yes. So no, that will error out. We need the object version when we pass into an array list. We need to pass in the wrapper class. What? So you're saying, yes, you can do that. Yes. So the idea here is, here we have, when we define an array list, right? If we're passing objects that aren't integers, if we want to define something like a dynamic type and a static type, we can pass in. What's that? Say that again. I think that would allow you to put in different objects depending on the type of static and dynamic type that you want to use. I mean, like, they're both valid, but yes. Okay. Okay, I'm going to go to the next slide then. So yeah, here we're going to talk about exceptions. So what are exceptions? So exceptions are ways for us to handle errors in our code when like certain conditions aren't fulfilled. So we'll do this within a catch block. So we throw exceptions, like so say if we throw exception E, after we run our catch blocks, the exception is thrown at the very end of our code. Okay, so what is the general instruction for exception handling? So the general instruction is a series of catch blocks. So you've seen this before, we'll go over this on the next slide as well. And then we also talk about a hierarchy of exceptions when we talk about exception handling. So the hierarchy of exceptions talks about how some exceptions are classified as within the general exception. So look at this on the next slide. So here, we have this hierarchy of exception, and then we have a null pointer exception here, and the array index out of bounds exception over here. So what we're saying here is a null pointer exception is classified as an exception, but an exception is not classified as a null pointer exception. Okay? So both these two are subclasses of this object here. Okay? So we have a sample here. So we have a try, where we try a random code, and then we have a series of catch blocks. So we have a catch for array index out of bounds, catch for a null pointer exception, and then a catch for general exceptions. So what would happen if we put the catch block of null pointer exception, or the catch exception here, so this exception here, before the null pointer exception here? Okay? So that would cause, I guess it's not incorrect, but if you did that, the null pointer exception that would come after the exception block would never happen. And the reason for that is because the exception would catch every null pointer exception before it got to the null pointer exception block. Okay, any questions about exceptions? Yes? Say that again?
Do we have to know like what kind of exceptions are checked and unchecked?
Can you give me an example, I guess?
Like I guess some exceptions you have to catch them because it's like checked or otherwise I think we
Do you know what he's talking about? No, okay. Yeah, I'm not really sure what you mean by checked or unchecked.
There's some you have to declare that like this method throws some exception or it won't like compile. But like
Oh, I see. That sounds like an error rather than an exception. Is that correct?
I don't know. I think like if you're like throwing an IO exception or something, you have to declare that like this method throws this exception and handle it in some way.
Oh, I see what you're
So
saying.
there's like some exceptions that like
Yes.
won't compile if you don't handle it.
I think, yes. Like this right here, like you can run the code here, and it would compile. And that's why you have to have exception handling in this case. You can also have exceptions to catch like compile time errors, I think. Yeah.
I think what he was asking is which do we need to know which exceptions like have to be handled or which ones can be like left alone? Because I know null pointer exceptions can like go unchecked and then
I see. I'm not sure how in detail Hog covered checked versus unchecked exceptions. But I think like whatever he covered in lecture, like make sure that you understand that. And then especially understand like this hierarchy of exceptions and how you throw exceptions and handle errors in your code. Okay, anything else? Okay, I think that's the extent of my slides. Lauren? All right. So let me give you this. Put this in your pocket, and then we put this in here, and then talk into this.
Okay. Okay, hi guys. I'm Lauren. I'm another one of the mentors, and I'm also on core staff. So to get started, I'm going to start talking about asymptotics. Asymptotic analysis is a method to describe the runtime of your algorithm with respect to the size of its input. So we represent our asymptotic analysis with 3 different symbols. So with big O notation, it gives an upper bound on the runtime of a function as the size of the input approaches infinity. With big omega, it gives a lower bound, and if your big O and big omega notations are the same, then we can represent it with big theta. So I'll give you guys like 5 minutes to get started on this problem. Sorry.
You always
Okay, so let's go over this question. So in the best case, we would find the start integer at the value index parameter, in which case it would just end in theta 1. In the worst case, we'd have to look through the entire array for the value, which is start in the parameter. And it works out because it just recurses until it finds it. Any questions? Yes. It would terminate in the shortest amount of time given a certain input. Why would a small array not count as a valid input versus a larger one or a medium-sized one? So do you understand that at the best case, we would hit the first if statement and the second one, and we would see that the element at the start index, if it's value, then it would just terminate? Yeah, sorry. Sorry? No. It depends on the function, right? Okay. So let's give the second one a shot. I'll give you guys 5 minutes to work on that. Oh, yeah, sorry. I can't hear you, so you have to speak up. In the worst case, why are we going by the upper bound and not the lower bound? Are you saying that why is it theta? Because your best case and your worst case isn't the same, right? So we would have to bound it by the upper bound. Because if I said, okay, I have at least $5 in my wallet and I have at most $5 in my wallet, which is more informative? Well, upper bound would be more informative, right? So we would always want to use the upper bound if we can't bound it by theta. Well, if the lower bound and your upper bound are the same, then we can say it's theta, right? Right, so we would go by the worst case, which is the upper bound.
I think what he's trying to say is that you provide more information if you lower bound it by omega of 1. Because then, because some functions don't have a bound of omega of 1 on the lower side. So if you can bound it on the lower side as well as the upper side, then it would sound better and look better because you have more information about it, right?
But your upper bound isn't bounded by 1.
What do you mean?
Like that's your lower bound.
Yeah.
Yes.
Yeah, why don't we put the lower bound as well?
Well, your worst case or your best case would be theta 1 and your worst case would be theta n. So you're describing that when you're saying your best case and your worst case. But when I ask you for overall, you would use upper bound or theta. Or theta, if if your best and worst are the same. Yes. Yes. Not the lower bound. Okay. I mean, you could put the lower bound if you wanted to. I don't think anyone's going to complain, but yeah. Yes. I'm sorry, I can't hear you. So you look if your best and worst case are the same, and if they're not, you would use the worst case as an upper bound. Sorry. Your overall would be your best case if they were the same. Right. Any other questions? Yeah. Okay, so for question 2, the trick here is that J is initialized outside of the loops. So even if we run the outer loop, running the inner loop is not guaranteed. So in the worst case, we have theta m plus n, and in the best case, we have theta n. To elaborate, for the best case, while iterating through the outer loop, we would never iterate through the inner loop, so which is why it's just n. And then in the worst case, we would run through both. Any questions? Yes.
If you change the break to return, the best case would be theta m instead, right? Because once the inner loop runs once, you would break return out of the entire function, and thus you would end at almost constant time. Wait, no, then it would be constant time. It would be right? If you change the break to return, it would be constant time, best case.
So how would break and return differ in this context?
The break here only breaks out of one loop. Return returns out of the entire function, and therefore, because if you break out of the inner loop right here, you still have to run the outer loop n times, which is why the best case here is theta n, which is why while iterating through the outer loop, we never iterate through the inner loop. That's the best case, right? So
Yes.
it would be theta 1 because best case would be theta 1.
Yes. Yes. Sorry, I'm sorry, could you speak up? Because here it would be defined in a different scope. So even if we increment it, it would never start over if we hit another iteration in the outer loop. Any other questions? Okay. So let's move on to heaps. Just some binary heap invariants. The tree must be complete. All available positions for nodes must be filled, except for possibly the last row. So essentially at every level, we're going to be filling it up from left to right. So we have the min heap property and the max heap property. I guess it depends on which one you're trying to implement, but the priority value for min heap of a node must be smaller than that of its children, and for max heap, it's just the opposite. So just a quick check just to make sure that you guys understand completeness of heaps. So the left one would be complete because you're filling it up from left to right. The second one would not be complete because the right child is there, but the left is null. Same thing for the third one. And then for the fourth one, it would be complete because everything is filled left to right. So for heap operations, first we're going to go over adding an item. So there are two steps. So you first put the item you're adding in the next available spot in the bottom row of the tree. And if the row is full, make a new row. And you would swap the item you just added with its parent while its priority is smaller than its parent, or until it is the new root. So essentially, you would just bubble up after adding in the first step. So let's go over an example. So let's say that you had this heap and you wanted to insert 5. So you would add 5 to the last row, and you would bubble up until it is in its rightful place. So there it is. And then if you insert 0, you would place it in the bottom once again, and you would bubble up until it's in its rightful position. Any questions about that? Okay, let's move on to delete. So to delete, you would replace the item at the root with the item in the rightmost spot of the bottom row. And this is just to maintain the completeness property. And then you would bubble down until it's in its rightful place. So just another example to illustrate that. If we were to delete 0, we would swap it with 5, and then we would bubble down until 5 is in its rightful place. Any questions there? Okay, so for runtime, for adding an item, it would take log n, average case, because we have to bubble up. To get the smallest, since it's at the top, it's just theta 1. And if we wanted to remove the smallest, it would also be theta log n because we would have to bubble down. Any questions there? Okay, let's move on to priority queues. So the whole point of talking about heaps is because they're usually used to implement priority queues. So priority queues have basic operations of, well, initializing, adding, removing, checking if it's empty. And there's also a peek method that gets the item at the front of the queue without actually removing it. So give this runtime analysis question a shot. I'll give you guys 2 minutes. Feel free to grab cookies. There's so many. Of course. No, take the last one. It's so lonely. No, I'm saying that the priority queue is implemented with an unordered linked list. As like, a priority queue is implemented with an unordered linked list as its underlying data structure. Okay, so if we consider the implementation of a priority queue with an unordered linked list as the underlying data structure, the worst case time to insert something into the priority queue would be theta 1. Because since we're using an unordered linked list, we can just attach it to the front, which takes constant time. Obviously, this is not a good priority queue implementation. Yes?
Why would you need a priority queue to do this then? Couldn't you just keep it as linked list? Because the priority queue, the purpose isn't it to sort things?
Well, I'm just saying that the linked list would be the underlying data structure to implement this priority queue, so it's kind of the other way around.
But my question is like, if you actually, so you don't care about the priority, is that what you're saying?
I'm saying that this is a very bad priority queue, but we're just saying that it is implemented. Yeah. Any other questions? I'll give you guys 2 minutes to look at this. It's kind of the same idea. Okay, so since when we inserted, we always inserted just randomly appending to the front without considering the elements inside of the list, removing an element would entail theta n runtime because we would have to look through every element in the list in the worst case. Does that make sense? Any questions? Okay. I'll give you guys 2 minutes for this as well. And the next question is the same, except you would find the runtime of removing. Yeah.
So how do you remove it?
Okay, so if we consider the implementation of a priority queue, but with this time, instead of an unordered one, we keep the ordering inside of our data structure, it would be theta n because we would have to search for the correct spot to insert the node since the list is ordered. Any questions there? So similarly, when we're trying, oh, I didn't include the remove one, I'm sorry, but similar idea. Okay, let's try this with balanced binary search as the underlying structure. It's quiet, so I assume you're done. So in order to insert something, in the worst case, it would take theta log n because the tree is balanced and we may have to travel all the way down its height to insert, and the height is log n. So similarly, when we try to remove an element, it is also theta log n because we would have to search all the way down to the left branch of the BST to find the smallest element. Any questions? Yes. Which one? Sorry, could you speak up? When we insert something into the middle, okay, so what would the runtime of that be? Sorry? Uh-huh. Um, I think it depends, or once we find, well, to find the position, it would be theta n, right? But to, oh, you're saying the insertion would be constant. Yes. If, well, I guess it depends on implementation as well, right? Sorry? Yes. Yes. Hashing. I think that's Tapan, you're up. Yeah. Here you go. Oh, wait. I will.
Okay, yep, so we're going to go over hashing now. Yeah, so we've gone over asymptotics, so I think we can go cover this pretty quickly. So yeah, what is the runtime of inserting into an array? So let's say if there is space in the array. So if there is space, this will take constant time. Now if there isn't space, this means we need to resize the array. So that means this takes linear time because we need to copy the n elements into a new array of a larger size. Okay, so you should know this. The runtime of a hash table, it's constant time. So why is this the case, and under what assumptions is the runtime of a hash table constant? So the reason for this is indexing it into the main array. So like we have our array here. This takes constant time. And then this, assuming our external chaining is small, we can keep our search in linear time. So when I say external chaining, I'm talking about this here. Okay? So if this chain outside here, outside of the bucket of the array is small, the runtime of the hash table, or finding an element in a hash table takes constant time. Okay, so let's talk about collisions. So what are collisions? So collisions are when we have multiple elements in the same array bucket. And then we have external chaining. So we talked about this, right? So external chaining is a way to handle collisions within our array. So generally we use a linked list. So if you see here, right, we have a linked list. But we can use other data structures. So like rather than a linked list, we could use like a tree, maybe like some sort of heap object or something. But there's, in this class, generally we'll use a linked list. And then we'll talk about the load factor. So what is a load factor? So a load factor is when tells us when to resize our hash table. So we resize our hash table when, so the load factor is a fraction, basically. So the fraction is the number of items over the length of the array. So when the number of items divided by the length of the array exceeds our load factor, that tells us we need to resize. So when we resize, we need to expand the size of our array and then reinsert every single object in our hash table into the new array. So this takes theta n because we have to insert n objects into our hash table, which each of these objects takes constant time, but because we're doing this with n objects, it takes theta n. And then we'll talk about a hash function. Okay, so the hash function turns our object or whatever thing that we're inserting into our hash table into an integer, and then this integer must be consistent for the object. So if we have two objects that are the same, they should return the same hash code, and ideally our hash code is unique. And we'll talk about this in a later slide, why it's important for the hash code to be unique. And then we have to turn our hash code into an array index. Okay, so we do this by using the modulo function to get an index value. So given a hash code x, we do x modulo array size, and we get some output. And this output correlates to our the indices of our array. So the range of outputs is from 0 to array size minus 1. Okay, so we're going to do practice problems. Does anyone have any questions of what I went over in the last 3 slides? Great. All right. So yeah, this is hashing practice. This is pretty easy. So like basically, we're inserting 5 into this hash table, and we're going to resize it by doubling the size of our array. So spend like 5 minutes, and we'll come together and get the answer. Okay. So we'll go over the process of solving this problem. Okay. So first, we need to find the hash code of every number that we're inserting into our hash table. So the problem said the hash code is the integer itself. So the hash code of this number 8 is 8, and we do 8 modulo 8 because the size of our new array is 8. So 8 modulo 8 is 0. So we'll do this with 25 next. So 25 modulo 8 is 1, 10 modulo 8 is 2, 18 modulo 8 is 2, 15 is 7, and we're inserting 5, and 5 modulo 8 is 5. Okay. Any questions about modulo? Sweet. Okay, so we're going to insert it to our new array. So this is what it looks like. So we double the size of our array, and then based off the hash code, that determines which array index we insert into. So here, just to note, 10 and 18 can be in any order. We didn't really specify that we go like incrementally through our external chain. Okay. Does anyone have any questions about this first question? Yeah.
So there's like never like any necessary order for things that have the same hash code?
Not unless specified. Maybe you have like some sort of stable hash table or something that has numbers in the same order, but usually you'll assume no. Yes.
So numbers like have like the hash code as like just themselves?
Not always. I think it really depends on the kind of hash code that you define. In this case, because the problem specified that the hash code of the number is its number itself, then it gives you that answer. But usually in any problem, like they'll define what the hash code is. Okay. Anything else? Okay, we're gonna do a harder problem this time. Take a few minutes, look at this. So we're gonna look at amortized analysis. Actually, there's a slide. We'll go over this talking about amortized analysis and kind of like how to solve these kind of problems. Okay, so I guess maybe I'll read it in case you can't see. So there are ways to resize a hash table that other than the way that we discussed in the lecture. For each scheme below, give the amortized lit best and worst case runtime for a single insertion operation in theta notation in terms of n, the number of items in the hash table. If the operation given could result in infinite runtime, write infinity or infinity inside the big theta. Assume the hash code function takes constant time. By the best case, we mean the set of items that are spread out nicely by their hash code, and by the worst case, we mean a set of items that have the worst possible collisions by their hash code. Define L to be the average number of items in each bucket, and assume resizing takes linear time. Okay, so let's go to the next slide. So let's talk about some review. What is the runtime of inserting into a hash table? And how long does it take to resize a hash table, assuming the hash table has n elements? So like we said before, inserting into a hash table takes constant time. And then if we need to resize, we exceed our load factor. That takes big O n, because we need to redefine our hash table and then reinsert n items into our new hash table. And then how do we find amortized runtime? So this is an important concept. Basically, amortized runtime is a runtime of n separate operations divided by n itself. And then for this purpose of solving this problem, let's say the size of our hash table is k. And for any k, the resize takes big O k time. Okay. So this next slide will go over the first problem. Take another more than 5 minutes to solve all 4 problems, and we'll come together and solve these together. What was that? Sorry? L is the load factor, yes. So remember, load factor is the number of items divided by the size of the array. Okay, so let's go over this together. All right, I'm going to go over the first one. Okay, so in this case, we need to see how long does it take to how long our runtime is with some number of insertions. So let's say with large K, right? So with large K, an addition, the worst case addition, which takes big O K time, will take place every 3K insertions. And these 3K insertions will take constant time. So this is the reason. The reason for this is because we quadrupled the number of buckets when the load factor is 1. So basically, every time we reach our capacity or the size of array, we quadruple the size. So basically, say if we have a size k array and we triple our the size of array, if we insert another 3k, we have to triple it the size of array or quadruple the size of array again. Okay, that's kind of confusing. Does that make sense? No. Okay, let's try again. Okay, so let's say we have k elements in our array right now, and our array is length k. So right now the load factor is 1. Does that make sense? Yes? Okay, I'm going to repeat that one more time just to make sure. So basically, we have k elements in an array, and our array is k long. That means the load factor is 1, and we've reached our maximum, the size of the load factor here. So we're going to quadruple the size of our array. So when we quadruple the size of our array, when's the next time that we reach a load factor of 1? When we add 3k right here, right? So when we insert 3k more items, then we reach our load factor 1 the second time, and we need to resize our array. So that's when we reach our most costly operation. Okay. Does that make sense now? Okay, sounds good. Now let's say in small k, for small k, the worst case addition will need to take place every insertion. So say if k is equal to 1, our load factor is 1 every single time, and then we add 1, and then we have our worst case runtime or an insertion of big O k. Okay, so using this formula where we say the time to add n objects divided by n, we have these two equations here, right? So in this equation here, this refers to the worst case for large k. So for large k, we do this worst case addition, which is big O k, and then we have to add 3k plus multiplied by 1. So this is the constant time addition here, which takes place 3k times, and this takes place, this worst case takes place every 3k times of the constant addition. Yes, this right here refers to the resizing here, and then this right here is the constant time operation when we have space in our hash table. When we're regularly inserting, okay? And we are inserting k times. Any questions here? Okay, so when we simplify this out, this all becomes big O1. And in the worst case, we have big O over 1, yeah. But if we do it k times, they become about the same. In the end, like this entire thing simplifies to big O and constant time. So it doesn't matter too much. But I just want to make sure that you understand that this is how you find amortized runtime. Okay? So this right here will simplify into big O constant time. And then this over here, this stays linear. Yeah. The worst case. So this worst case, this is for small k, right? So say if we have a hash table with 1 item in it, and our array is length 1, right? We have to resize our hash table. So in that case, the resize of the worst case operation happens after 1 addition. So when we do 1 addition here, we only do 1 resize, which is big OK. Yes, but I guess in this case we're talking about like a range, and we're talking about for small k. So when we do the small k, we have to do we assume the worst case. We do a resize. Yes.
So on the left, in the left equation,
Yeah.
Dividing it by k.
Yeah.
Explain why you're dividing by k.
Because we're doing about k insertions.
For every k insertion.
Every k insertions to get the next resize, I guess, right?
But
Yes, you're right. That should be 3K. But regardless, like this will still get you the right answer. So every actually it should be, yeah, it should be 3K.
So it's 3K on the bottom, right?
3K, yes, 3K on the bottom. You get a 3K plus 1 or something. In the end, like yes, this entire thing will simplify into big O constant time.
And like,
Yes.
what's the 3K on the top?
3K times constant. So this refers to 3K insertions when the hash table has space. So when our hash table has space, it takes constant time, and we do this 3 times, 3K insertions, before doing a resize, which takes big OK. Yes? Big- Yes, that's another way to think of it. Yes. That's correct, yes. Yes, that would, it's like another way to think of the worst case. Yeah. Okay, yes. So this is in the case where we do 1 insertion, and we get a worst case like having a resize of 1, having a resize after 1 insertion. Okay, so like in this case, like we said, like the runtime for inserting n items divided by n. N can be any number. In this case, we're saying n is 1, and if n is small, if k is small, we have a resize right away. Yes. Sorry, what was that? This is the first item, the only item. Only item that I'm inserting, and if you say it again. What was your question? Yes, that's correct. This isn't like in a worst case where like we insert 1 item and we have to resize our array.
But if it's for the same like K is infinite, very large, then like the amortized
The amortized should be constant like we have here. So depending on the size of k and the range of our n, we'll get a best case and worst case. Okay, yes? So when I say this worst case addition refers to, the worst case addition is when we have to resize our hash table. Okay, so we're resizing our hash table this time when we have big OK. Say it again. Because if we have a large K and we have a large range, we don't have to resize as often. And yes. Okay. Yeah. So a range can be anything, right? N can be anything. So say if n is 1, we'll get a worst case like this. Okay. So we'll go to the next question. The next one is like pretty similar. Yeah, so basically in this one, same kind of thing, right? Except in this case, we double this, the length of our array for every L over 100, L 1 over 100 insertion, with a load factor of 1 over 100. All right, so we'll do the same kind of thing where we have a resize for big OK. So when we have this resize of big OK time, we add, for every K over 100 insertions, these K over 100 insertions take constant time. Okay, so when we do K over 100 with constant time insertions with 1 resize, we end up with a constant time amortized analysis. And for the same reason as before, we have a linear time of big O over 1. Okay, this is really similar to the first one. Okay, so let's go over to the next one. I think this one is different. It's a good problem to do. So in this case, we increase the number of buckets by 10 every time our load factor is 1. So every time we have the same number of elements as the size of an array, we have to increase the size of an array by 10. So the worst case resize will take place every 10 insertions regardless of the size of our array. So for small k or for large k, we resize our array by 10 every single time. Okay? So let's look at what this looks like. So in this case, for every 10 insertions of a constant time addition, we do one resize. So that's why we have big O k plus 10 multiplied by the constant time addition divided by 10 itself. And then when we do this all, simplify it down, this becomes big O linear time. Yes?
Could you go back to the previous slide real quick? Yes. Why is the bottom not k over 100 but k here?
This could also be k over 100. You could say k plus k over 100. In the end, like the ratio will still be the same. It really depends on how you define your problem.
But that's more correct, right? Because here it's for every single k over 100 insertions, do you resize plus k over 100 new insertions?
Yeah, I think you're right. Yes. So this should be k over 100. But like in the end, like I'm also like considering this as like a ratio. So like for every k insertions that you do, k over 100 constant time insertions will get you a resize. Okay. We'll go back to this. So yes, this right here, just to recap, right? So we have 10 constant time insertions plus 1 resize. This all simplifies down into linear time. So this applies to both our best and worst case scenarios because we do this for small and large k. Okay. Any questions about this one? Okay, great. We'll go to the last one. Okay. So for this one, we have kind of like an interesting way to resize our hash table. So we double the number of buckets until no bucket has more than 5 elements. Yes? Because this is every 10 insertions, we resize, this is in the worst case. This worst case resize will take every 10 insertions, we resize the size of our array. Because in this case, we're this worst case addition will take place every k over 100 insertions, right? So in this case over here, the worst case will take place every k over 100 insertions because that's when we double the size of our array. Sorry, can you say that louder? Louder? Yes. Are you talking about this problem right here? Over 10. Because we increase the number of buckets by 10 when L is greater than 1, right? So when L, L refers to the load factor, okay? So say if we have a hash table with k elements, and then we resize it. So now we have an array of k plus 10, and then what is the max number of elements that we can have in our hash table before we have to resize again? Yes, k plus 10. So if we insert 10 more elements, then we do about 10 constant operations plus 1 resize. So simplify, that's why so like the formula for amortized analysis, right? It's the time for n operations to adding n operations divided by n itself. So in this case, adding 10 operations takes about big O, or a resize, plus about 10 constant operations divided by 10 itself. Yes? That was because the number of buckets is related to the number of insertions that we do before the resize. In this case, because we're adding a constant number of 10, that's why we're dividing by 10. Yes? Yes? Yes, you're right. It would be k over 100, but it also depends on how you define your problem for amortized analysis. So in this case, it should be k over 100 in this case. But if I wanted to do k, it would also work, and we'd still get the same answer. Yes, exactly. The numbers will all cancel out. Okay. Any questions besides of this one? We're going to go on to the next one. Okay, great. So yeah, the same kind of thing. So let's talk about the best case. So the best case is similar to our first two problems, how we scale our the size of array by some constant. So in this case, like we do this worst case resize every k insertions, and similar to the same two problems like parts A and B, we'll get the same best case runtime of big O constant. Okay, you can kind of verify this like the same way that we did parts A and B. Yes.
So for all the four problems that you described here, you always use advertised time for the best case, but then you only specify the case where you resize for the worst case. Why is it that? Why do you only consider advertised when you consider a best case insertion, but you don't consider advertised time when you consider a worst case insertion that resizes?
Because you want to consider, that's a good question, right? So the question is, why use a really amortized analysis to get a best case bound, I guess. And the reason for that is because we assume that the less costly operations of like inserting in constant time will lower our average or this cost of our resize.
Why does that not apply to your worst case?
Yes, they're both like kind of amortized, but we consider a bound that gets us a better solution.
But if you amortize the worst case, it will still be constant. Because the worst case insertion, even if it happens, overall, it seems like it's constant.
Yes. Well, I mean, like we want an amortized bound in the case, like considering the worst case insertion, I guess.
No, I understand why advertisement is that way, but why do you only use that on your best case situation when you should be using it on all the cases, and therefore making everything advertised?
Yeah, I think it's overall using advertising cost, but and according to the question, the worst case means you have to.
We're adding to the same bucket every time. Yes.
So in this case, the reason it's theta k is not because it's not because of the runtime. It's because of the way the hash function is set up, and also the way the hash table is set up. So it's because you need to look through all k elements and insert it. Is that what you're saying?
I think according to the question, that's all about BST.
Let's look at the worst case, and then maybe that will answer your question. Okay. So in the worst case, right? So in this worst case, we talked about this hash function, right? So this hash function, say if we have a chain of 5 in our first bucket, and every time we resize, we always have a chain of 5. How many times will we need to double the size of our array? An infinite amount of times, right? So say if we have a chain of 5 in our, we have a constant hash function. So we have a constant hash function that puts all our elements into the first bucket, and every time we resize, we always have that all 5 elements there. So we'll have to keep doubling our array, and we'll never end our resizing operation. So that's why in the worst case, we have an infinite runtime here.
For the previous question.
Yes.
Sorry, we were talking about the previous question, like the example before.
Okay, what's your question?
You had theta k as the worst case or something.
Concerning the worst case addition.
So why don't you consider amortized time for that? Because like you consider amortized time for the other one.
I see what you're saying, yes. It's the same kind of thing, right? So like an amortized bound of like how, you can set a bound of how much you want.
But technically I could say best case is just constant time, like just looking at one insertion that doesn't have any resizing.
Yes, you're right. But I think like in this case,
Because you have to take it to infinity, so you can't just look at like one and not consider like how much it spans.
but I think I'm talking about like the size of k will determine how often you need to resize. We can talk about this after. Like I need to really get through these slides. But yes. And after that, yes, I just want to go over like these are the solutions for all 4 parts. And yes, I think that'll be all our hashing problems. If you have questions, you can post on Piazza or meet up after the review session. But yeah, I think this is Allison.
How does this work?
So put this one in your pocket. Your mug.
Okay.
And then just put that in your, yeah.
Okay, hi everyone, I'm Allison. We're going to talk a little bit about BSTs. So a BST is a binary search tree. So this is basically just a tree in which I'm defining an order. So to the left are elements smaller than a specific node, and to the right are elements larger than that node. So to the right, I have an example where 3 is the root, and 1 goes to the left because 1 is smaller than 3, and 5 goes to the right because 5 is greater than 3. Average runtime is log n when we assume that our tree is balanced, which we'll talk a little bit about tomorrow. So we're assuming log n because we're assuming that a height of our tree is average case log n. Any questions before we jump into our first example? Cool. I'll give maybe like 3 minutes for this question. Cool, so let's go over the solution for this question. There are two possible solutions. One is moving the 19 up, and one is moving the 23 up. So just to explain a little bit more about why we chose those two nodes, 19 is the greatest element that is to the left of 20. So we know that if we move that 19 up, we don't have to change anything on this side. And we also don't have to change anything to the right because we know that everything to the right must be greater than anything that was to the left. Question? Right, so that would take log n because worst case we'd have to traverse all the way to the bottom. And to explain the other solution, we would just be moving up this 23, which is the smallest element that is larger than 20. So the same as the other side, we don't have to change any of the other elements on either side if we chose those two nodes. Any questions? Yes? So the for reference changing is, so the first two references are the two from the root. So because we're changing this, we're moving this 20 out, we have to change these two references. And the other references would just be moving either this 18 up or this 24 up. So basically we're just saying like we don't want to have to restructure our whole tree. Any other questions? Cool, let's move on. So in this practice question, I've made this ordering of letters on the right-hand side. Just to be a little bit more specific about it, these letters are not in alphabetical order. So what we're going to do is we're going to fill in this tree on the left-hand side based on this ordering I've made on the right. I'll give maybe 5 minutes for this. Okay, we're a little quiet, so I'm gonna go over the solution. So the way that I'm gonna approach this is I'm gonna fill in this bottom tree, largest to smallest element. So the first thing I'm gonna notice on this side is like, where is the largest element, right? So I'm gonna start from D and I'm gonna go right, G, but I can see that there's a larger element A here, right? So from A, I know that P has to be smaller than A, so that means that A is the largest element in this tree that I've given. So based on that, I can fill in this node up here with A. And the reasoning for that is because everything in this tree is to the left of this top root node, so we know that the top node must be the largest element. Any questions before we continue to fill in our tree? Cool, so next we're gonna find the next largest element. So going back to the original tree, we're gonna go right from D again, right from G again. We already filled in with A, and we can see that P is less than A, but because P is to the right of G, we know that P must be the next largest element. So where should we put P in this tree, right? So we're gonna go to the left of A, and we're gonna try to go as right as we can. So we're gonna go right here, and we're gonna go right here. So we know that P must fill in this box. So continuing like this, we're gonna find the next largest element. So we've already filled in A, and we've already filled in P, so we're gonna go to the next largest element, which is G. In our empty tree here, let's find where the next largest blank is. So we go from A to the left, and we're gonna try to go right again. And we know that this box has to be smaller than this box, and we've already filled in this box, so we know that G must go in this box. The next largest element in our original tree is D, and we know from our blank here, we went right to get to G and left to get to this box. So we know that this box must also be larger than this box. So D is going to go in this bottom box. Moving on from D, we're going to go and try to go as rightmost as we can again. So we know that B must be our next largest element. And B will go in this box, just same reasoning behind the rest of them. And then the next largest is E, which will go here. And Z will go in our empty box. Any questions on how I got this solution? Cool. Alternatively, you could also go the opposite way, where I fill it in from the smallest to the largest. But I just chose to go from the largest to the smallest because we can already see that this empty box was the largest element in our tree. Okay, we're going to talk about balanced trees, like 2, 3 trees and LLRBs tomorrow. So we'll let you all out 15 minutes early.
All right, so thank you so much for coming. It's been a really good review session. Please come to our review session tomorrow too. We're gonna be covering post-midterm 2 material. So that's gonna include 2, 3 trees, LRBs for tomorrow, as well as really hard graph questions, sorting, so that's all for tomorrow. We realized that it is at the same time as the HKN review session, which is from 6 to 9. Ours is 7 to 10, but you're gonna have to make the choice for yourself. I personally do not know what HKN will be covering, but we will have cookies. We'll have more chocolate chip cookies. So hopefully I will see you guys here tomorrow. Same place, same time. So thanks for coming. I clarified a little bit on the engineering student report sleep question. So if you visit that slide, I just made the changes like an hour ago, and I just put a little clarification note. So my bad for the bad question, but have a good night, guys. Get home safely.